So we'll go to another question that you guys sent to us, and I'm going to be a little bit quicker now because I feel like you now get the point about what is happening here. So I hope you're going to be with me and follow suit as I actually work with this thing. So the next question comes from Maile. Maile, this is your question. Thank you for sending it. It's one that doesn't involve numbers. It's got variables on it, and I hope you guys are going to be able to cope as we work with this, because the mathematics does not change. Just because you're not working with numbers anymore, it doesn't mean that the rules are going to change. So I'm going to be a bit quicker as I work with this one, and I hope you're going to be following as we are working with this. So the question reads as follows. There's a framework for a construction that consists of a cyclic quadrilateral, right? PQRS, which happens to be on the horizontal plane. So there's a cyclic quad on the horizontal plane, right? There is a cyclic quad on the horizontal plane. Now, we're going to have TP as shown in the figure from point Q to P is actually going to produce an angle of elevation which is given by y degrees. Okay, cool. So it's not easy for you to follow as I read here because you can't see the diagram. So let me plot the diagram down for you so you guys can follow what is going on here. So apparently we've got a cyclic quad, which means there's a circular shape that we have on one plane, which happens to be the horizontal plane. And then we've got points on this. There's a point P there, there's a point S at some point, there's a point R, and there's also another point Q here, right? There's P here, there's S, and then we've got R, and we also have Q here, right? So these happen to be points. Doesn't look like a circle because of the way we are drawing this, or we are viewing this from a different angle. When you're viewing this, it looks weird. It doesn't look like a circle, but it's actually a circle that lies on the horizontal plane. Now there is a pole here. There's actually a pole, a horizontal pole that goes upright like that, that is connected to point Q, and at the top it is T, and then obviously this is going to produce an angle of 90 degrees because the horizontal plane is always perpendicular to the vertical plane. Okay, cool. Now the other information that is given here is the fact that this side here is equal to that side, and they're both K units. That's K units, and this one is also K units. We are also told that the angle here, this angle here, is apparently 2x, right? And we are told PT is equal to 3 units long. And the last thing that we are told is that this angle here, this angle that you see here, it's called the angle of elevation. It's apparently y units. That's y units. This is what we call the angle of elevation, right? The angle of elevation is y units. Okay, now the first question reads as follows. These are the questions that we need to worry about. The first one says we need to show, right? We need to show that PSQ is actually equal to x. We need to show that angle PSQ equals to x. All right, fine. So let's see what we can do in this. We need to first of all identify where is this angle PSQ, right? Angle PSQ is this angle that is on that cyclic quad we're telling you about, right? It happens to be this angle here, which I'm going to label as angle S1 to simplify things for me and for you guys to see what is going on. The other thing I'm going to label is angle Q there. I want to call this one angle Q1 because they are my angles of interest, since they lie in the triangle that has got a lot of exciting things that are going on there, right? Now, trigonometry, even though it's trigonometry, it doesn't exist in isolation. So sometimes we require you to go back to your geometry and borrow the knowledge from that and use them in order to solve the questions that you're currently working with. So for example, in this question, I was told that there's a cyclic quad. So this question is not even a trigonometry question. So sometimes you guys struggle with these questions, not because you don't understand the trig, but because you forget that the other concepts of math might play a role in this. So they said it's a cyclic quad. What do we know about a cyclic quad? We know that opposite angles of a cyclic quad always add up to 180 degrees. So that is actually my line of thinking. So as I look at this, I know that this angle that I'm looking at here, that angle R and that angle P, when you add them, they're going to give you 180 degrees because they are opposite angles of a cyclic quad. So that's where I'm going to begin. I'm going to say to you angle SPQ added to angle R will always produce 180 degrees because these are opposite angles of a cyclic quad. This is information from grade 11. That's why it's important for grade 11s as well to join in when we're doing these things, because there's a lot of what they stress about that is appearing in grade 12, and they might learn a lot about using those ideas as they move on. So this one that I'm looking for is SPQ. I don't know what it is, but I know for a fact that angle R is apparently 2x, and this must give us 180 degrees. And then if I apply witchcraft mathematics, my angle SPQ is going to be 180 degrees minus 2x when this angle is subtracted on both sides. When you subtract 2x on both sides, you're going to end up with 180 degrees minus 2x. So what does that mean? That means now I know the value of this angle, which is 180 minus 2x. Now, the beauty about the triangle PSQ is that it's an isosceles triangle. Now, in an isosceles triangle, you only need to know one angle to find all of them, because two of those angles are equal to each other. And in this case, angle S1 is equal to angle Q1 because they are both opposite sides that happen to be equal. And this information was also in the statement. So I'm going to first of all start by arguing that those angles are equal. So I'm going to say to the examiner, my angle S1 is equal to angle Q1 because those are angles that are opposite equal sides. Right. Okay, fine. They are angles that are opposite equal sides. Now, in that triangle that you're looking at, in triangle SPQ, I'm going now to add angles of that triangle SPQ. S1 added with angle Q1 added with that 180 minus 2x must give us 180 degrees because they're interior angles of a triangle. So I'm going to say to the examiner, angle S1 added with angle Q1 added with 180 degrees minus 2x. They need to give us 180 because these are interior angles of a triangle. Very important. Now, since S1 and Q1 are the same, I can start calling Q1 S1 because I'm interested in finding S1. So I'm replacing my Q1 with S1 because Q1 and S1 are identical. So I'm going to call this one S1, right? S1 plus S1 equals 2. And then I'm going to then deal with these guys by subtracting them on both sides. So it's as good as saying we're transposing 180 and we're also transposing that negative 2x. So I'm going to end up with 180 degrees minus 180 degrees plus 2x. And when you add S1 and S1, you're going to get twice. Angle S1 is equal to twice x, and by dividing both sides with 2, we end up with a value of angle S1 is equal to x, which is what we had to prove. Now, good practice in mathematics is after finding stuff, get into the habit of writing these things on the diagram. So I'm going to move now and replace my S1 with x because I now know that the value of S1 is x. Let's just clear here inside. I know that S1 is x, and by extension we can also call angle Q1 x because both of them are actually equal. Right. Let's move on to the second last part of this question. We are now required number 2. Right. Number 2 says we need to prove that SQ, we must now prove, this is where trig comes in, prove that, right, SQ equals 2k multiplied by the cosine, right, of x. Prove that SQ is equals to 2k times cosine of x. Okay, cool. So where is this SQ? First of all, we need to identify where SQ is. SQ is, I'm going to draw it in green now, happens to be this side here, right? It's this side that is in the middle of our cyclic quad. So the examiner is interested in finding the length of that particular side. Now, if you look there, it's basically part of a triangle that has got a length of k here and another length of k here that has an angle of x inside and another x inside. And we also know that this is 180 degrees minus 2x, and we are looking for that length, which is what the examiner is labeling as q. So we are looking for that. Now, in this case, I've got a lot of information on my triangle. I've got more than 3 things that I have. So I can actually use the sine rule to figure out what the length of SQ is going to be. Okay. And I'm going to work it out here on the side. So what I'm going to say is in that triangle there, in triangle SQP, the side that is opposite this P here is what you call small p. That small p is opposite to what you're looking at, which is what we want. So small p divided by the sine of angle P has to be equal to maybe small q divided by the sine of angle Q. I can pick any 2 of them and compare them. Remember, the sine rule compares all 3 sides of that triangle, but we don't need all of them. We just need to compare 2 pairs. Cool. Right. Now, my small p here is the side that is opposite angle P, which is the SQ the examiner is interested in, divided by the sine of the angle of interest. Now, the angle opposite to that happens to be 180 degrees minus 2x. Right, minus 2x. Now, that is equal to the side small q. Small q is the side opposite angle Q, which is k, divided by the sine of the angle that you see there, which we have found to be equal to x. Right. Now, once I'm done with it, I'm then going to try and simplify by engaging our trigonometric ratios, you guys should know that in trigonometry you can apply what we call reduction formulas to reduce this part of sine 180 minus 2x. And according to our trig ratios, we can then say that SQ divided by the sine of 2x, because 180 minus 2x is just going to be as good as the sine of 2x, is equal to k divided by the sine of x. Okay, from here I'm then going to simplify that part. Let's just see what we can do. I'm going to remove what I have here because we have seen what is going on with this, so we have space. Right, so I'm now going to simplify by cross multiplying. You don't need to do both those ratios. You can just cross multiply this part alone. It's still going to work out just fine. So this is going to be SQ, right, is equals to k multiplied by the sine of 2x divided by the sine of x. Now this here is what we know as a double angle identity, which we know the expansion of to be 2 sine of x multiplied by the cosine of x divided by the sine of x, which has always been on our denominator. And then from here, of course, I can then cancel things that divide each other off. For example, sine will divide sine out, so this one is gone. I'm left with 2 times k. The best way of writing things like this is to start with the number. So I'm going to have 2k multiplied by the cosine of x, which is exactly what we were required to prove here. So I hope this helps you to see what is going on, particularly if you are dealing with triangles that happen not to be right angle triangles. Then you need to engage your sine rule and your cosine rule, and this probably is going to be the best way of explaining. I could have used the cosine rule as well to solve this, but the sine rule does also do the trick. Remember, your double angles, when you see them, expand accordingly. You guys should know that the double angle of cosine expands to what, and the double angle of sine also expands to that. In addition to that, you also need to know your basic algebra plays a big role here. Cross multiplication, addition of like terms, those kinds of things might be a problem if you are handling these kinds of questions. Even your trigonometry doesn't exist in isolation. It works hand in hand with Euclidean geometry. So keep that in mind as well. It's very important. I hope this has helped you to understand what is going on. We're waiting for more questions, guys. Keep sending them through.